Hello, and thank you for joining us on Space Nuts, where we talk astronomy and space science. Great to have your company once again. And coming up on this particular episode, we're going to talk about an exoplanet that has unusual rain. It's raining gemstones and ruby slippers. Well, maybe not the ruby slippers, but definitely gemstones, which is very unusual. We're going to do a James Webb Space Telescope update, which is something new for us. And a quadruple asteroid system has been discovered by a group of people in Thailand. So that's fascinating. We'll also be answering some audience questions. Bob wants to talk about research papers and how accurate or otherwise they might be. Al is asking a question about a black hole becoming a singularity, and is that possible, because he doesn't think so. And Steve is asking questions about photons and black holes. We're starting to leak back towards the black hole phenomenon, starting to dominate again. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
My name is Andrew Dunkley. I am your host. Thank you for joining us. And with us again this week, because we can't get rid of him, really, it is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you?
You are the Space Nuts barnacle. You are.
Yeah, I know. Just a barnacle on the backside of Space Nuts. Oh dear. Oh, well. It was ever thus. It was ever thus.
Yeah.
I've been a barnacle. In fact, I'm probably still a barnacle on the Department of Industry, Science, Energy and Resources as well. They can't get rid of me either.
Yeah, why would they want to, Fred? To be honest?
Thank you.
Why would
that's
they want to?
That's a nice comment, yes.
Right, we've got a lot to talk about today, so let's get straight to our first topic, and this is a really interesting one. We've talked about exoplanets and even planets and moons in our own solar system that have unusual kinds of rain, like sulfur rain and acid rain, and I think we talked about a planet once that rained diamonds. Now there's an exoplanet that rains gemstones. What's this all about?
Well, yeah, it's gemstones among other things, and it's there's a lot going on this exoplanet. What is it? Well, it is. I think it's a WASP. Yeah, WASP 121b. WASP is a project that detects exoplanets by the transit method, the fact that their brightness drops when they pass in front of their parent star. WASP 121 is actually a star which is about 850 light years from here. It has a planet which is very close to it. It's a hot Jupiter. That's the the official description, because it's a big planet. And it orbits its parent star once every 30 hours. So, its year is 30 hours long, Andrew. It just beggars belief, doesn't it? But that's what's happening. Now, that means, one of the things that means is that with a period that short and a distance between the parent star and the planet that small, this planet will be tidally locked to its parent star. And that is the key to understanding what's going on here. It is its day side always is permanently facing the parent star. Well, that's a bit of a tautology, really, isn't it? Because the day side is always facing the parent star. But the bottom line is, this is a good start this morning.
You're going well, Fred.
The bottom line.
See how I bailed you out of that?
Yes. Oh, well done. Thank you. Yes. The planet is rotating at the same rate at which it revolves around its star, like the moon is rotating at the same rate as it revolves around the Earth. And so you've got this one side of it that permanently faces the heat source. And that means one side is hot and the other side is cold. Now, given that we can't see these planets directly, you may well ask, Andrew, how can you study the day and night sides of a world like this in detail?
That's a good question. Glad I thought of it.
I'm glad you thought of it too. And the answer is it's really clever stuff and needs, it needs really quite significant astronomical infrastructure in order to make these observations. I should mention that the authors of this work come from MIT, Massachusetts Institute of Technology, Johns Hopkins University, Caltech, and other US universities.
It is a mouthful, but it is Massachusetts.
Massachusetts is what I tried to say. That's right. I didn't really. Anyway, never mind. I didn't do well with it. But so how do you detect what's going on the day and night sides of a world like this? And what you do is you observe the planet, and all you can see is the star. That's the only thing that is visible in your telescope.
Yep.
But you observe the star's light throughout the orbital period of the planet. And given that that's only 30 hours, you don't have to wait very long. If you were looking from outside the solar system and trying to do this with Jupiter, you'd be waiting, 12 years or something like that? Much longer. No, I think it's 5 years. Sorry, I should do that calculation again. Anyway, 30 hours gives you time to, to actually work out exactly what's going on through the different phases of the planet, because that's what it's all about. It's like the phases of the moon. We watch the moon going round because it's lit up by the sun, and we can see, it progressing from new moon to first quarter to full moon and all the rest of it.
Yeah.
And you can do the same thing with an exoplanet, but all you're able to measure is the total light from the planet plus the star. But as you'd imagine, that varies throughout the revolution period of the planet. When the planet is behind the star, all you've got is the light of the star. And I should add that you're not just observing how bright it is, you're also observing the spectrum of this thing. So you're looking in detail at the chemical constituents that is revealed by the light that is coming to you.
Yeah.
So when the planet's behind the star, all you're seeing is the light of the star. When the planet shifts slightly in its path around the star, so you can see both, what you've got is effectively you're looking at the full planet, like equivalent of a full moon. It's almost completely illuminated.
Right.
And that light adds to the light of the star. And so you can then look at how the spectrum has changed. And that is telling you about the atmosphere of the planet itself, rather than the atmosphere of the star. In fact, what you can do is subtract the stellar spectrum from the spectrum of the combined planet plus star, and you get the planet spectrum. That's how this works. And then that changes throughout the planet's year, 30 hours. And eventually you're looking at the backside of the planet. And in fact, you have a point where that is superimposed on the star. Once again, you can do some clever work, because you can look at the combined spectrum of the backside of the planet superimposed on the star itself. That combined spectrum, if you subtract out the spectrum of the star itself, it shows you what chemical constituents, again, are in the atmosphere of the planet, because the light of the star is passing through the atmosphere of the planet, round the edge of it, and coming back to Earth. So that's the technique. And what's been found is that this object is quite extraordinary. So it's got a day side that is extremely hot, more than 3,000 degrees Kelvin. So what that does is it's known that there is water vapor in the atmosphere of this planet. Well, there's water vapor on the night side, but on the day side, the water molecules are just torn apart because of the high temperatures. So you've got hydrogen and oxygen atoms that are they're independent within the atmosphere. And then it turns out that because of the heat, that generates high pressure in the day side, which causes winds that blow things around to the night side. And on the night side, it's cool enough, for these things to form back to water. And so you get water vapor forming in the atmosphere of the dark side of the planet. They estimate that these winds are 5 kilometers per second.
Oof.
So this is 11,000 miles per hour. It's 16 to 17,000 kilometers per hour.
Sounds like that's the same as it was in Sydney yesterday.
Yeah, we didn't get the wind, but we got the rain.
Good.
So we got the water vapor. Huge quantities of rain. Oh gosh, bucket loads of it. H2O suitably combined back into water vapor.
Yes.
So that's what they get on the dark side of this WASP 121b. But wait, there's more, because it's not just water that's circulating like this. They find that on the night side, the temperature is right to have quite, I guess the best word is exotic, clouds of exotic materials, and iron is one of them, and a mineral that actually is a constituent in gemstones. That's the point that you were making right at the beginning.
Yeah. Well, that's the journalistic hook, isn't it?
It is, absolutely. So, yes, to quote the physics.org report on this, on the way around, exotic rain might be produced, such as liquid gems from the corundum clouds.
Wow.
So, liquid rubies, that'd be quite nice, actually.
Yeah, again.
Anyway, really quite remarkable stuff. I should mention that these observations were made with the Hubble Space Telescope. It was one of the spectroscopic cameras on board the Hubble telescope that was used, and fantastic work. Congratulations to the team and to the journalists who are writing about this.
I don't suppose they can tell us exactly what kind of gemstones these might be, or gem components.
Yeah, they're suggesting that it could be maybe. Look, I had rubies in my mind, and yeah, maybe rubies and sapphires.
Wow,
that's the possibility. Corundum apparently is a mineral that goes towards these gemstones.
So I wasn't far wrong with my ruby slippers analogy.
No, it's a very nice one. That I like that very much. Yes.
Interesting. All right. That's a fascinating discovery. And if you want to read more about it, you should go to the phys.org website. That's not FIZZ, that's PHYS.org website. It's a fabulous website if you want to catch up on that and many other stories. Now, while we're still up in space talking observations by telescopes, there's one called the James Webb Space Telescope that popped up in the news recently. Haven't heard much about it, to be honest, but they've been trying to sort of put it all together and get the parts all linked up and get that mirror all organised. They've been taking some test photographs. We talked about one last week with the star that came out in 18 images. Has there been any progress since then?
There has, Andrew, yes. And it's part of the process of, harnessing this mirror from 18 segments to a perfectly focused single surface mirror, making beautiful images of different distant objects. So what we saw last week was 18 images of a star in the constellation of Ursa Major in the Northern Hemisphere, which were completely randomly placed in the field of view of the camera. And that was great because all 18 were there, so that the mirror segments were somewhere near where they ought to be. What they've done now is they've tidied that up so that you've got this lovely hexagonal pattern of these 18 images. And doing that actually expedites the process of, first of all, focusing each of the segments independently to give you a perfectly sharp image, and that will still result in this display of 18 different images in a hexagon, but that hexagon will kind of match the positions of the mirrors that have formed the image, if I can put it that way. It's just a ready way of identifying which star has come from which segment. When they've focused all the segments, you'll get perfect star images from each segment, and then the work will begin to bring them all together so that they make a single image. That's the final stage of the process.
Yeah, I'm looking at the image compared to last week's, and you can see the improvement in the alignment. They're really starting to come together well.
It's great. The process is called segment alignment, and the final stage, when they've got that right, and each star is focused, or the star from each segment is focused, then they do what's called image stacking, which, as its name implies, they put all the 18 image segments on top of one another to make a single image.
Well, I know a bit about that. I haven't tried it, but a few people I've been chatting with about astrophotography of late have been telling me about some of the methodology that they use and image stacking. Some of them actually take, rather than photos, they take videos of the images, and then they work that into a still picture using the data that they've built up. There's some clever people out there. I'm not one of them, but
well, you are. You're following in their footsteps.
Oh, I'm trying to. Some of it I find way out of my league, but I'll catch up eventually.
That technique. So what you do is you take a video which consists of many, many still frames, and this is mostly for observing planets. Actually, I have to say, and what's happening during that period is we're not talking about the James Webb now, folks. We're talking about Andrew's backyard. But the atmosphere varies, and occasionally within that video there will be images where what we call the seeing, the amount of turbulence is virtually zero. So there's the perfect image, essentially. So what you can do is you extract the perfect images from your video and then stack those together. You get almost a what we call a diffraction limited image. And I might just add that technique, which is called lucky imaging, was invented by a friend of mine by the name of Craig Mackay at the University of Cambridge. He did this on professional telescopes 25 years ago. And his lucky imaging process is now basically carried out by amateur astronomers because he can do it. It's fabulous stuff.
Fantastic. It's well named too, because it makes sense that if you take a series of stills, within a few seconds, you could have hundreds of images, and because 30 frames per second is about average these days, isn't it, or something?
That's right. Yeah. So you have thousands of images, of which
you're going to get lucky. Yeah. In that regard, rather than taking, like my camera takes 5 shots. I've set it up to take 5 shots of a single press, and I could get lucky there too, but probably not as lucky. Makes sense. Yeah, it's good. And I should have known that you'd be connected to somebody who came up with the idea.
Yeah, I'm afraid that's right.
All right.
The small world is the astronomy world. That's the answer.
Yes, I imagine so. Small world, talking about a very, very big world.
Big universe, yes.
This is Space Nuts with Andrew Dunkley and, of course, Professor Fred Watson.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
Now, if you would like to do us a favour, that would be wonderful. You can send your checks to Fred Watson Of course, if you do want to become a patron, you can do that, and that is putting a little bit of money into the kitty to keep the podcast rolling, which you can do via our website. Now, that is totally optional, and thank you to those many patrons that do so through Patreon or Supercast. So that's something that you can do, or you can make one-off donations through the Buy Us a Cup of Coffee button on our website, spacenutspodcast.com. Or if you want to do something that's going to be cost-free and just cost you, a bit of time, write a review through whatever podcast platform you happen to use. So that's very helpful as well. So those are some of the options to help support the Space Nuts podcast, and we do appreciate anything anybody does to keep us up and running. Now, Fred, we have a very interesting story out of Thailand, which I found most surprising. When you talk astronomy and research and discovery, you don't generally default to Thailand. A beautiful country. I've visited it, and lovely, lovely people. They're some of the nicest people on the planet, to be honest. But a few researchers from the National Astronomical Research Institute of Thailand have announced this discovery. Now, this is sort of a new spin on an old discovery, from what I've read.
Well, yeah, that's right. It's a new discovery. Yeah, Thailand's actually got quite an active astronomical community, Andrew. I've colleagues who, in fact, one in particular who works there, and a number of others who've been there working. This is 3 researchers, one from Thailand, 2 from France, at the Université de Lyon and the Université Sorbonne.
Righto.
Yeah.
That's pretty good, Fred.
In Paris, yeah. We aim to please. Anyway, what they've done is they've used the Very Large Telescope down there in Chile, which is, of course, operated by the European Southern Observatory, and to which our Australian astronomers also have access because of the strategic partnership that was signed back in 2017. I've always got to plug that, and it's great. It's excellent that we've got that. It's amazing to think that strategic partnership between Australia and the European Southern Observatory is now halfway through.
Yeah,
2022. It's staggering how fast time flies by when you're having fun. Anyway, back to this asteroid. It is a well-known asteroid. It's number 130. Electra was discovered back in 1873, and it's been known actually for almost 20 years that it had at least one moon. That was discovered in 2003. Another one 11 years later in 2014, and now another moon. So this is it makes the asteroid a kind of quadruple object, because it's an asteroid which is relatively large. It's 260 kilometers across. It's a decent sized object.
Yeah,
but it has 3 moons. So altogether, it's a quadruple object, having 4. What staggers me about this, Andrew, is just the fact that, these scientists have been able to observe these moons, because they are a long way away. This asteroid is actually in the outer region of the main asteroid belt. So it's not a particularly close one. It is something called a G-type asteroid, and they're quite rare, in fact. They're carbonaceous asteroids, which are relatively common, but these are a particular subgroup of those, and it's about 5% of all asteroids are G-types. And in fact, the most notable and the biggest is Ceres, the dwarf planet Ceres, which was the first asteroid to be found. So what I was going to say was, what is staggering, given how far away this object is, Electra, is how small these moons are. First moon is reckoned to be 6 kilometers across. The second moon discovered is reckoned to be 2 kilometers across. And the third one, the one that's just been discovered, is actually 1.6 kilometers across, about a mile. It's very, very small. And when you think something, a mile across at that distance, the far edge of the asteroid belt, that is astonishing stuff.
Yeah.
It's really extremely good work. They've done a lot of clever image processing, but the moon is definitely there. Actually, now I found a statistic which I thought was quite remarkable. This little object, the new one, is very close to Electra. Its orbit's quite close to the asteroid itself, and its brightness is 15,000 times less than the brightness of the asteroid.
Wow! So
you've got something, it's the old comparison of trying to spot the cigarette end of the lighthouse keeper while he's on the platform next to the lighthouse.
Yeah.
It's that sort of, huge difference in brightness. So they've done very, very well to tease out the light of this little moon orbiting around asteroid Electra.
And Space Nuts does not endorse smoking in
smoking. No, it's a difficult. I tend not to use that.
No, I was just joking.
But it's hard to find a better. It's a really good. It's a really good example. Yeah. Although don't worry, I'll think of something.
Oh, maybe a torch or
you could say
flashlight,
is mobile phone.
mobile phone light. Yeah,
Yeah, the mobile phone.
but no, I understand what you're saying. Makes sense.
Yeah.
Now, I just need to clarify something in my head because I get confused about this. When you say the asteroid belt, this is out beyond Mars?
Yeah, between the main belt is between Mars and Jupiter.
Right.
That's correct.
Okay.
So, and this is on the far edge of that. So it's, its distance is really quite significant.
Because the other one's out around, it includes Pluto, right?
Yeah, that's right. That will be the the Kuiper belt or the trans-Neptunian objects and all the different categories of objects that are out there. But yeah, it is a very distant asteroid belt. So I guess the three main regions where there are asteroids are, first of all, the main asteroid belt, and that is by far the most populous. And then the Trojan asteroids of Jupiter. These are the ones that orbit in Jupiter's orbit and in front of and behind Jupiter. And then, the trans-Neptunian objects, the objects way, way out in the furthest reaches of the solar system.
Yeah. So there's all these layers in the solar system that sort of live in little regions as you spiral out. And
yeah, that's right.
So we've kind of got a divide between the rocky planets and the gas giants, haven't we?
Yes, that's right. And that's exactly right. And it's once again, it's because Jupiter's such a big planet. It's probably, the main asteroid belt is remnants of the formation of the solar system. And they've kind of been steered there just by the gravitational influence of Jupiter. It's probably more or less where they formed, but they're still there. Jupiter's huge gravitational pull may well have inhibited the formation of another planet there.
Yeah.
So we've got this debris.
It sort of reminds me of flat pack furniture, Fred, because the formation of the solar system, and there's got all this leftover stuff. When you get flat pack furniture and you put it together, you go, hang on a minute. What is that? What am I supposed to do with this? Where does this go?
Yeah, and when you realise where it should have gone, you're really too far down the track to take it to bits.
Yeah, don't worry about it. If we ever move, I'll fix it then. Yeah,
more or less. Yes, that's right. Put it in the box. All right, and forget about it.
But yeah, what a great discovery, and delightful to hear that there was involvement in Thailand, because I don't think too many people would realise that they've got an astronomical fraternity, if you like.
Yep.
Fred, thank you so much, as always.
Great pleasure, Andrew. Thank you. And we'll speak again next time.
We will indeed. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thanks for joining us again. Great to have your company. Keep those cards and letters rolling in. We love snail mail. We might get it in a couple of years. But until next week, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.